Hello, everyone. Welcome to this optional session on the convergence of iterative policy evaluation. So, as I said, we're going to cover a really fantastic proof. I think it's the most interesting proof that you see in a reinforcement learning course, usually. Um, Now, the proof is quite involved. So, if you really want to understand it in depth, it will take you a considerable amount of time, and it's been quite a while since I've looked at this proof, so I'll also probably have to struggle a little bit to remember all the details. So let's start with some very simple definitions. So let me first define what is a norm. So consider a vector space Z over some field F. So the most common vector space that you're probably all used to is the vector space of vectors, of d-dimensional vectors, real vectors. And the usual field is the field of real numbers. So this vector space Rd over the field of real numbers allows you to work with real vectors that you can add to each other and that you can multiply by real constants. Right? So if you don't recall, a vector space is basically a set together with some operations on the elements of these sets that have to be closed, meaning operations between, for example, the addition between any two vectors must also be inside the vector space. If you multiply a vector by a member of the corresponding field, that element also has to be a member of the vector space, and so on. Um, so that's a vector space. So these are the most common vector spaces and fields. Um, Now, a function that maps an element of a vector space to a real number between 0 and positive infinity is called a norm if it follows all of these three, if it obeys all of these three statements for all vectors u and v in the vector space and every element of the uh, field. Now, the common norm that you're probably all used to in is the Euclidean norm for a vector space of real vectors. So a norm has to have these three properties. So the norm of a sum of two vectors has to be less or equal to the norm of the first vector plus the norm of the second vector. This, when the norm is Euclidean, this is actually called the triangle inequality in general. So how do you interpret it in Euclidean space? Well, if you think about a vector and another vector, and you think about adding to this vector here, that would result in this vector here. And what this is saying is that the length of the vector that results in adding these two vectors has to be less or equal to the length of the first vector plus the length of the second vector. So this is the triangle inequality, and it basically tells you that the shortest path in Euclidean space is a straight line. Another rule that norms must obey is that if you take let's again think about the Euclidean space. The next rule is that a member of the field A times a vector, the norm of that must be equal to the absolute value of the element of the field times the norm of the vector. So in our Euclidean space, this can be interpreted in the following way. So if you take a vector and you scale that vector up by a constant, the length of this scaled vector, which would be given by this term, needs to be exactly the absolute value of the constant by which you scale the vector times the original length of the vector. Okay. And finally, we have one last rule, which is that if a vector v has norm 0, then that vector must be the 0 vector. Now remember that the 0 vector from a vector space is that special vector that when you add to any other vector results in the original vector. So if you have any vector u and you add to it v, and v is the 0 vector, then the result of that must be u. Okay? So that's the definition of the 0 vector of a vector space. So if a vector has norm 0, then it must be the 0 vector. In other words, the only vector with norm 0 is the vector 0. Okay, so I already gave you one example of norm, and that was the Euclidean norm, which you're probably all used to. And you can write down the Euclidean norm in the following way. So if you have a vector v, the Euclidean norm of this vector v, which is denoted in this way, is the square root of the sum of the elements of this vector squared. Okay, so if you have this vector here, you just look at its x-axis component, you look at its y-axis component, you square them, you add them up, and you take the square root, and that's the length of the vector, and that comes from Pythagoras, this theorem, of course. Okay, but there are other interesting norms, and actually for our purposes, we'll not look at the Euclidean norm at all, so don't be confused. We will actually be mostly concerned with something called the maximum norm. Now, the maximum norm for a vector space composed of real vectors is defined in the following way. So the maximum norm of a vector v, denoted in this way, is the maximum across all possible elements of these vectors of the absolute value of those elements. So you're going to look at every element of a vector. Let's say, for example, we have the vector 2, minus 3, and 1. What would be the maximum norm of this vector? Well, you'd look at the values, all the values of this vector, of the absolute values of each of the elements of this vector. So the absolute value of 2 would be 2. The absolute value of minus 3 would be 3. And the absolute value of 1 would be 1. And because this is the maximum absolute value, you would say that that is the maximum norm of this vector. Okay. So intuitively, the maximum norm tells you what is the element with the largest absolute value inside a vector. Okay. So you can actually test that all of these properties hold. We are not going to do that, but it's actually pretty easy to show that this is a norm. Notice, for example, that the only way for a vector to have maximum norm 0 is if it's all of its components are, all of its elements are 0. So we've defined norm. Now we are going to define a convergence in a norm. Okay. So suppose that you have a sequence of vectors. So let's denote the sequence by v0, v1, and so on. And this can be an infinite sequence of vectors. We say that this sequence, again, we denote a sequence. We can denote a sequence in this way. And this represents a sequence of vectors like this. We say that a sequence converges to a specific vector v in the norm, in this specific norm, which we denote by Vn converges in this specific norm to V, if when n tends to infinity, the norm of the difference between Vn and V is equal to 0. Okay? That's how we define convergence of a sequence in a specific norm. So what does this limit actually mean? Well, this limit means that um, there exists an n such that for every n larger uh, than n, there is an for any epsilon that we pick, there exists a delta such that the difference between Vn and V uh, in norm is less than epsilon. Um, so I actually didn't need this one. So again, the limit um, the limit with n tending to infinity of the norm of the difference between Vn and V being 0 means that for that there exists an n, a capital N, such that for any lowercase n larger than that n, for every epsilon, the difference in norm between these vectors is below that specific epsilon. So at some point, for any epsilon that you pick, you can pick, there will be an n such that when you look sufficiently, when you look at every element that follows n in the sequence, the difference between that element and this vector v in norm will be less than epsilon. Okay? Now we are ready to define something called a Bellman operator. So I noticed that I made a small mistake here. I should have said that for every epsilon larger than 0, this is the case. So let me just go through this one more time. So the limit when n tends to infinity of the difference between the norm, of the difference between the limit when n tends to infinity of the norm of the difference between these two vectors being equal to 0 means precisely that for every epsilon larger than 0, there is an n such that for any n, for any lowercase n larger than n, the norm of the difference between these two vectors will be below epsilon. In other words, no matter how small you make this epsilon, but still above 0, I can find an n such that Vn will become arbitrarily close to V. Okay? So now we move to the Bellman operator. So Bellman operator will help us define something that we need in order to look at policy evaluation. So consider a reinforcement learning task. And for convenience, we're going to say that this task has states 1, 2, up to a number of states that we'll denote by the cardinality of this state S. And suppose also that we number our actions from starting in 1, and then 2, and then 3, and so on. And so we have a finite number of states and actions. And suppose that we have a discount factor, which, as we know, must be below 1. To ensure that the expected return, the expected discounted return is always, is never infinite. Now, for any vector v that has as many elements as we have states in our problem, in any state S, the Bellman operator, which maps vectors that have as many states, as many elements as we have states in our problem, to other vectors that have as many elements as we have states in our problems, is given by the following. So before I explain this to you, what we are doing here basically is we are using vectors, real vectors, to represent values of states. That's what we're going to do. So we've already looked at value estimates for states as multidimensional arrays, so this shouldn't be a surprise to you that we can, for example, imagine that we have this vector and that the first element here represents the value uh, under a specific policy of the first state, and here we have the value under the same policy of the second state, and so on. So this is what we're going to do. We're going to use vectors to represent um, estimates of value of states. Okay. So let's start again from the beginning. Consider a reinforcement learning task where we have states number from number 1, 2, and so on, and actions 1, 2, and so on, with some discount factor. Then for any vector that will represent or some estimate of value for all of our states, and a specific state S, the Bellman operator, which maps one estimate to another estimate, will be given by the following. So for each state S, if you index the result of applying the Bellman operator to a vector, so remember, the Bellman operator will take a vector as input, and it will output another vector. And so what we're looking at here is at a specific element, the element number S of the vector that results from applying the Bellman operator to another vector. And that element S will contain the following. It will contain an expectation over all actions of the probability according to this policy pi of taking an action in that state, times an expectation over S prime, next state S prime, of the probability of transitioning from the current state to the next state given this action that comes from this expectation, of the immediate reward of transitioning from between S and S prime with that action, and the estimate, the current estimate for the value of S prime derived just from V. So notice that the Bellman operator is basically implementing this operation that we defined in when we talked about policy evaluation. So this step of updating an estimate vk into an estimate vk plus 1 can be represented by taking a vector that represents vk and transforming it into a vector that represents vk plus 1. So this is precisely the role of the Bellman operator. The Bellman operator is a function that when you apply to a vector gives you the estimate for the next step in a policy evaluation algorithm. So in other words, the Bellman operator is just something that happens inside the policy evaluation algorithm. Okay. So now we are finally able to state the theorem. So we have not, we are nowhere close to a proof of the theorem. We are only ready to finally state the theorem that we are going to prove. So what we want to prove is the convergence of iterative policy evaluation. So I want you to consider the Bellman operator for a specific policy pi. So notice that the Bellman operator, in order for you to apply it, you need a policy, you need to know the function p, and you need to know the function r. Okay, and you need to know also the discount factor, and then you have everything that you need to compute your estimate, your next estimate based on a current estimate v. Okay, so consider the Bellman operator for a specific policy that will map estimates of values of states to new estimates of values of states for that specific policy pi. Now, suppose that you are given an arbitrary initial vector. Remember, policy evaluation can start with an arbitrary estimate, and this would be your arbitrary initial point for policy evaluation. Now, consider the sequence of vectors that you would obtain by deriving the next vk plus 1 from applying to vk the Bellman operator. So this is the sequence that you obtain by taking your initial estimate, applying the Bellman operator to get the next estimate, applying the Bellman operator to get the next estimate, applying the Bellman operator to get the next estimate, and so on. So remember, this is precisely what policy evaluation does. So consider the Bellman operator for a specific policy. Suppose that you start on an arbitrary point, and suppose that you compute this sequence in the way that policy evaluation computes it. And now consider a vector that basically represents the actual value function for the policy pi. So this is the vector where each element contains the value for a specific state under the policy pi. So this is the vector we're looking for with policy evaluation. And now, so consider this vector, which you're going to represent by v pi. And this is the vector such that v pi of s is equal to v pi of s for any s. Then these are the things that we are going to prove, and as such prove the convergence of iterative policy evaluation. We're going to prove that Vn, this sequence here, converges in maximum norm, so not Euclidean norm, it converges in maximum norm to v pi. So eventually, what I'm saying is eventually that sequence v0, v1 will eventually get arbitrarily close to v pi, and arbitrarily close. What I mean here is that this limit when n tends to infinity will be 0. We will also prove along the way that v pi is a so-called fixed point of the Bellman operator. So a fixed point is simply is any vector such that when you apply the operator to it, you remain at that same vector. So this operator does not transform the vector. It maintains the vector as it currently is. So we're going to prove that v pi is a fixed point of the Bellman operator for pi. So this means that whenever we have the correct estimate for the value of all the states under a specific policy, when we apply the Bellman operator again, we're not going to destroy that estimate. That estimate is simply not going to change. And finally, we will prove something about the speed of convergence of this sequence. So basically, we're going to prove that the element number n of this sequence, that its maximum norm, that is the maximum norm between the difference of this element and the correct value function for pi, we're going to prove that that is less or equal than gamma to the n times the the maximum norm of the difference of your initial estimate and v pi. So what does this mean? This basically means the following. So this is basically the distance in maximum norm between your estimate at a given time step n and the correct estimate. And this side is telling you, is basically saying your initial distance, the distance between where you started, your initial arbitrary estimate the um, and the correct estimate times gamma to the n. So what this means is that when gamma is very small, let's say very close to 0, when you take it to the power of n, um, this number will truly become very small. And as such, no, even if you start very far away from the correct estimate, you soon become very close to the correct estimate. So after n time steps, this distance has to be less or equal than this distance. So if this distance is, so if this term is very small, sorry, not this distance, if this term is very small, then the distance between these things has to be very small after n time steps. Okay, so this is just the statement of the theorem. So to prove that, and I hope that I have convinced you that by proving this theorem, I will have proved that policy evaluation uh, converges. So again, what are the steps? Consider that you have a Bellman operator for a policy pi, and suppose that you have a sequence of vectors that correspond to applying this Bellman operator sequentially to the elements in the sequence. And let's denote by v pi the vector that we're looking for, the vector that represents the actual value of each state under the policy pi. In that case, what I will show to you is that the sequence of vectors converges in maximum norm, so it becomes arbitrarily close to the vector v pi that we're looking for. I'll also prove that v pi is a fixed point of this Bellman operator, meaning that once I have the correct estimate, the estimate is not going to change anymore. And also I'm going to prove that the convergence is relatively fast, meaning my distance after n steps to the correct estimate needs to be below the original distance, the distance from my initial estimate and the correct estimate times gamma to the n. So because gamma will always be a number between 1 and 0, this convergence must be relatively fast. So before I get started on proving that theorem, we need to go through a couple of definitions. The first definition is the definition of a Cauchy sequence. So let's consider a normed vector space. So this just means a vector space together with a norm. So you can imagine here, for example, that you're looking at a real vector space and the maximum norm. We are going to say that a sequence of vectors in this space. So if you take any sequence that you can imagine of vectors in this space, you're going to say that it's Cauchy if it obeys the following. So if the limit when n tends to infinity of the supremum for m larger or equal than n of the absolute value of Vn minus Vm is equal to 0. What does this mean? This is slightly tricky to interpret. So first of all, maybe you're not familiar with supremum, so you can just think of supremum as meaning maximum. It's slightly different. So the supremum is by definition the largest number, the smallest number that is largest in all the numbers in a set. That almost matches the definition of the maximum, but it also works when a set does not have a maximum. If that's not clear to you how that could happen, you can just completely ignore what I just said and just imagine that you have maximum here. Okay, so what we are saying is that the limit when n tends to infinity of the maximum difference between Vn and a vector that comes after Vm, sorry, between Vn and a vector that comes after Vm in the sequence is 0. So let's once more take a look at what this means. So here, basically, we're looking at the maximum difference in norm between a vector Vn and a vector that comes after it, called Vm. So if so basically, a sequence is Cauchy if for every epsilon larger than 0, there is an n such that for every n larger or equal to n, we have that, let's say, the maximum sorry. We have that the maximum difference in norm between the vector Vn and a vector that comes after it is smaller than epsilon. Once again, I can pick any epsilon larger than 0, and I can guarantee, if a sequence is Cauchy, that there exists an n such that for any n larger than that other n, the maximum difference in norm between a vector Vn and a vector that comes after it is lesser than epsilon. So basically what this is saying is that at some point, this difference between an element of this sequence and an element that comes later, that comes after it in the sequence, basically the difference vanishes. So there is no longer a significant difference between a vector and a vector that comes after it for some n. Okay, so if you look deep enough into the sequence, you find that at some point the difference between an element and the elements that come later becomes kind of insignificant. That's the intuition for a Cauchy sequence. Now, in the way that I said things here, you're almost probably ready to assume that every Cauchy sequence converges to a specific vector, right? Now, that's actually not true for vector spaces in general, but it is true for Banach spaces. So a Banach space is a normed vector space where any Cauchy sequence is guaranteed to converge in norm to some vector v. Okay, so maybe you kind of already assume that a Cauchy sequence, as I defined it, converges to a vector, converges to a specific vector. That's not true in general, but that's true for a Banach space. So a Banach space is a normed vector space Z and some norm, where if you take any sequence that is a Cauchy sequence, then that Cauchy sequence will converge in that norm to some vector v. Okay. So for any d, for any dimension of so for example, let me give you an example of a Banach space. Okay. So for any d, for any dimension, the d-dimensional space of real vectors with the Euclidean norm is a Banach space. So every Cauchy sequence in this normed vector space converges to some vector, and the d-dimensional space of real vectors with a maximum norm is also a Banach space. Okay. So once again, what's a Cauchy sequence? A Cauchy sequence is one such that at some point, if you compute the difference in norm between a vector and a vector that comes after it, that difference is insignificant. And a Banach space is one where every Cauchy sequence converges in norm to a specific vector. And these are two examples of Banach spaces. Okay, so that's a lot of definitions. We need one more definition and one lemma before we are able to prove the main theorem that we are looking for. Okay, so one more definition. This is the definition of an L contraction. So consider a norm vector space, so it doesn't need to be a Banach space, but just consider a norm vector space and a function t that maps vectors into vectors from this vector space. Now this function t is said to be L Lipschitz if the following holds. So if the norm of the difference between transformed vectors u and v is always less or equal than L times the difference in norm between these two vectors u and v for any vector. So if for any vector u and v, applying the transformation to the first vector and subtracting the transformation applied to the second vector and taking the norm, if that's always below a constant L times, below or equal a constant L times the difference between these two vectors in norm, then T is called L Lipschitz. Okay. And if L is less than 1, then T is also called an L contraction. So what's the interpretation here? So basically what this is saying is the following. Suppose you have a vector u, and suppose you have a vector v. Now suppose you compute the distance between these two vectors, which would be, this would be the distance between the two vectors. And now suppose that you transform these two vectors in some way. So let's say, for example, that you're going to scale these two vectors. And so you're going to transform them a little bit. Now let's compute the distance between the transformed version of these vectors. The distance will be this one, okay? So this is an example using as a norm vector space R2 and the Euclidean norm, okay? So this term here would be the distance between the original vectors, which are represented by this black line here. And this would be the distance between the transformed vectors, that would be this side here. So I'm telling you that a transformation like the one that I apply to each of these vectors is an L contraction if the distance between the transformed vectors is always less or equal than a number less than 1 times the original distance between the vectors. So this transformation that I applied here is an L contraction because I've clearly shrunk because clearly if I apply this transformation, which is just scaling by a constant between 0 and 1, each of the vectors, clearly I'm going as a consequence to shrink. So the distances of between the transformed vectors will clearly shrink in comparison to the distance between the original vectors. That's why this transformation that I applied here would be considered an L contraction. But of course, for it to be considered an L contraction, it has to contract every single pair of vectors given to it, okay? So one last time. If you have a norm vector space and a function that maps vectors to vectors, this function is L Lipschitz if the distance between the transformed, the distance according to this norm, so if the norm of the difference between these two vectors, so if the distance between the transformed vectors is less or equal than L times the distance between the original vectors, that's the definition of L Lipschitz. And if L is lesser than 1, then T is also called an L contraction. Okay. Okay, so uh, let's finally prove something after all of these definitions. So I'm going to prove to you the following lemma. So if you have a normed vector space Z with some norm uh, here, and you have an L-Lipschitz function T and a sequence of vectors in this space, if this sequence converges to a vector V, then the sequence of transformed vectors also converges in norm to the transformed V. So basically what I'm saying is if I have a vector, this sequence here, let's say V0, V1, V2, and so on, and I'm telling you, hey, this sequence is eventually going to converge in norm to a vector V, then it is the case that the sequence TV0, TV1, TV2, this sequence is also going to converge in norm, but to, of course, the transformed V. Okay, this is the lemma that we need to prove, although it seems quite intuitive, right? Okay, so let's see the proof. By the way, I do require that this function be L-Lipschitz. Okay, that's when this holds. This I'm going to prove that this holds when this function is L-Lipschitz, not in the general case. Okay, so by the definition of an L-Lipschitz function, um, if I apply this function to any element of my sequence and I subtract um, from applying t to an arbitrary vector v. So remember that if a function t is L-Lipschitz, then for any two vectors that I choose, the distance between their transformed versions has to be less or equal than a constant times their original versions. Okay, so this must hold because t is L-Lipschitz. So for any, so consider an element of the sequence. So this would hold for arbitrary vectors vn and v, but I just happen to choose a vector that is inside my sequence and the vector for which I want to show convergence. Okay. And now, because I'm assuming that Vn will converge so that my sequence will converge in norm to V, I can say that that the limit of this term here when n tends to infinity is 0. Why? Well, because the limit of this term when n tends to infinity can be written as L times the limit of this term, because this term does not depend on n. And by definition of convergence in norm, this is 0. And so we have L times a limit that we know is 0. So that's 0 as well. Okay. So we know that now that this term here, when n tends to infinity, is 0. Now, we also know that the limit of 0 when n tends to infinity is 0. And because we know that the limit of this term here when n tends to infinity is 0, we know by the squeeze theorem that the limit of this term when n tends to infinity also must be 0. So if you don't recall what the squeeze theorem is from calculus, it basically tells you that when you have inequalities like these, and you can show that the limit of this term when, for example, an n tends to infinity is 0 in this case, and when the limit of this term when n tends to infinity is 0, because the limit of this term will also have to be 0, because it must be between the limit of these two other terms. That's the squeeze theorem. If you're not sure about it, you can always take a look at my notes on calculus that I mentioned before. Okay, so we've proved what we seek to prove, because this this statement tells us that TVN converges in norm to TV, which is what we wanted to show. So we wanted to show that if we had a norm vector space and an L-Lipschitz function and a sequence of L vectors in this space, then if this sequence Vn converge in norm to V, the sequence given by applying the function t to each of these vectors in the original function would converge in norm to TV. Okay, so we proved that, and now we finally can prove the central theorem that will allow us to prove the convergence of policy evaluation. This theorem is called Banach's fixed point theorem. It's a very important theorem. So let's look at what it says. So suppose you have a Banach space. So remember, a Banach space is a normed vector space where every Cauchy sequence converges to a specific vector in the norm of that space. So if you have a Banach space and you have an L contraction on this Banach space, so now we are saying that T is an L contraction. So this here for this term, we only said that we needed an L-Lipschitz function. Now we want an L contraction, meaning meaning that we are shrinking. When we transform vectors, we are shrinking them in the sense that we've discussed before. So if you have a Banach space and an L contraction on this space, so a function that maps vectors from this space into other vectors of this space that is also an L contraction, then T will have a unique fixed point, V. So there will be a V such that when you apply this L contraction to V, it will result in V itself. And furthermore, this V will be unique. So there will be a single vector that when transformed by your L contraction will result in itself if you have a Banach space. Furthermore, we are going to prove the two more things in this setting. We're going to prove that if you have a sequence of vectors and this sequence starts at an arbitrary vector of your space, and you keep applying successively this the transformation. So if you start at a vector v0 and you obtain the vector v1 by applying your transformation to v0, and you obtain the vector v2 by applying a transformation to vector v1, and so on, we are going to prove that applying the transformation t in this way leads to convergence to the vector v that is the fixed point of the L contraction. So again, you're in a Banach space and you have an L contraction. We're going to show that this L contraction will have a unique fixed point, so a unique point that the transformation maps to itself. And furthermore, if you start at an arbitrary point and you keep applying this transformation, you're eventually going to reach that unique point, meaning you're going to converge in norm to that unique point. And for any n larger than 0, the distance between an element n of this sequence here and your fixed point will be less or equal than L to the n times the distance between the initial point and your fixed point. Meaning if you're very close to your fixed point when you start the sequence, then the distance after n time steps must be less than that distance times L to the n. And so we must be very, after n time steps, we must be pretty close to it if L is, for example, if your factor L in the contraction here is a number between 0 and 1. Now, this already sounds to you pretty much probably like the statement that we wanted to prove regarding the convergence of policy evaluation. And that's not a coincidence. Basically, once we prove Banach's fixed point theorem, I'll come back to the statement of this theorem of the convergence of iterative policy evaluation, and you see that everything follows. All right, so let's prove Banach's fixed point theorem then. So the first thing that we are going to do is that show that the sequence that results from successively applying our transformation is Cauchy. And because we are in a Banach space, that will guarantee that the sequence is going to converge in norm to some vector v. Okay? That's the first step in the proof. So as a first step, we are going to show that for any n and k, the distance, and when I say distance, I will always be talking about the difference in norm of that vector space. It's just easier to think about it in terms of distance. So we're going to show that for any n and k larger or equal to 0, the distance between the vector n plus k and the vector vn will be less or equal than L to the n times vk minus v0. So meaning the distance between the vector, the initial vector and the vector vk times L to the n will be always larger or equal than the k steps that I would, than the distance between vectors vn plus k and vn. So here we took k steps to go from v0 to vk, and I'm computing the distance, and I'm telling you that this distance times L to the n is larger or equal than the distance of taking k steps between n and n plus k. Okay. Now the case when n equals 0 is trivial. So why is it trivial? Well, because when n equals 0, we simply have to prove that vk minus vn is less or equal than L to the n times vk minus v0. And remember that this, so we basically have the same, sorry, that this should be v0. So we basically have this same term on both sides here. So if this term is non-zero, we can divide both sides by this term, and we will just have to check whether L to the n is larger or equal to 1. And because n is 0, this would be equivalent to showing that 1 is less or equal than 1. So we showed the case for n equals 0. Now we are going to use induction to show that this is true for an arbitrary n. So we're going to assume that the inductive hypothesis is true for some n, and we're going to try to prove that that will then hold to the case n plus 1. So, but the way we define the sequence, remember that we define the sequence as the iterated application of this function t. So the element, so we can write for an arbitrary vector vn plus 1 in this sequence, we can write it as t applied to the previous element vn, and we can write vn plus k plus 1 as the transformation applied to the previous element, the element vn plus k. So the distance between these two transformed vectors we know from the definition of the L of an L contraction must be less or equal than L times the distance between the original untransformed vectors. Okay? And now by the inductive hypothesis that we had, remember that we had the inductive hypothesis that that this would be the case. So if we just, so we know from the inductive hypothesis that the distance here must be less or equal to L to the n times this this distance, which is what we are doing here. So finally, we have shown that for that assuming that the inductive hypothesis is true for some n, then we have also the desired result for n plus 1. So we proved it for 0, for the case n equals 0. Then assuming that the hypothesis is true for some n, we are able to prove that it will also be true for n plus 1. Now, moving on, we're still trying to prove that the sequence that we're looking at, the successive application of the R transformation, is Cauchy. The next thing we're going to note is the following. So first of all, notice that for any k larger or equal to 1, the distance between Vk and V0 can be written in the following way. It can be written as the distance so what we're going to do here, we're going to employ a little bit of a trick. So we're going to, so notice that when I take an arbitrary vector in my sequence Vk plus 1, and I subtract the vector minus Vk plus 1, this term is 0, right? So let's suppose that I basically both add and subtract every vector on the way between V0 and Vk inside this norm. So this will all add up to the vector 0 in the end, which will not change the distance between. So basically, I can include, I can add up a vector 0 here to this norm without changing the norm itself. And so I'm introducing all of these vectors on the way between Vk and V0 inside the norm in this way. And it will become clear soon why we would want to do that. Okay? Again, we're going to just think about the norm of the difference between Vk and V0. And we can introduce these useless terms inside this norm. That will allow us to write the norm of the difference between Vk and V0 in this way here, where we basically start our summation with I equals to 1 until k of Vi minus Vi minus 1. So if you think about this summation here, this summation is expressing precisely what we've seen here. And if it's not clear to you, we're basically just grouping terms in a slightly different way. So you're grouping the first term, Vk, with the term minus Vk minus 1. We're grouping the term Vk minus 1 with the term minus Vk minus 2, until we get to the end where we'll group the term V1 with the term minus V0. So this is just another way of expressing this sum up here. And now it will become clearer why we wanted to introduce these useless terms. Well, now from the triangle inequality, we will be able to say that, remember that the triangle inequality told us that if we had the norm of the sum of two vectors, that norm should be less or equal than the sum of the norms of the individual vectors. And this is precisely the result that we use in this step. So if it's not clear to you why the triangle inequality applies here, well, it's very simple. You can think that you can write down u minus v, right, as u plus the vector minus v. And then it becomes clear that the triangle inequality must still apply in a similar way. And so from the triangle inequality, we are basically able to move the norm inside the summation by introducing this inequality. And from the earlier results, so from the result that we just saw, from the result that we just proved, which is why we proved it in the first place, we were able to show them that earlier that the norm of the difference between the vector vn plus k and the vector vn was less or equal than L to the n times the difference in norm of the vector vk and the vector v0. So that's precisely the result that we are going to apply here. And we're going to say that this quantity is less than this quantity. Okay? Less or equal than this quantity. And finally, we are going to note that this norm here is completely independent of the indices in the summation, so we can move it outside the summation. And then we are going to note the following. If we added up L to the n from 0 to n, when n tends to infinity, this would be 1 over 1 minus L. So this is the, if you don't recall, this is the this comes from the formula for the sum of a geometric series. Okay, so we know, so suppose we push this norm outside here, we can know for sure that this value here would be at most, even if we picked k tending to infinity, it would be at most this value. So therefore, when we multiply 1 over 1 minus L by this norm here, we are guaranteed to be above this number here, because even in the extreme case when we have k very large here, this summation here would be bounded by 1 over 1 minus L. Okay, so what we proved so far is that Vk minus V0 is less or equal than V1 minus V0 in norm over 1 minus L. So we are now quite close to showing that our sequence that results from applying their transformation over and over is Cauchy. So what else do we need to do? Okay, so combining the previous two results, we can show that for any n and k larger or equal than 0, 0 will be less or equal than Vn plus k minus Vn in norm. Why? Because a norm can never be between two vectors can never be below 0. Now remember that for any n and k, we have shown that this inequality holds. So this is what we are writing here. So this must be less or equal than L to the n times the norm of the difference between Vk and V0. And we have also showed that the difference in norm between Vk and V0 must be less than V1 minus V0 in norm over 1 over L. So we're just multiplying that by a constant L to the n. So we have these inequalities here. So as a consequence, for any fixed n larger or equal than 0, I know that the maximum over all k's of the difference in norm between Vn plus k and Vn must be smaller than this. Basically, I'm looking at um, basically I'm saying that because this value must be smaller or equal than this value, the maximum for all k uh, of this value must be smaller or equal than the maximum for all k of this value. Okay, this is a step that I'm performing here. But notice that this is actually a constant with respect to k. And so I actually know that the maximum over all k of this distance between Vn plus k and Vn must be smaller than this constant always. So it should be clear to you that we are now very, very close to showing that the sequence is Cauchy. So notice that now let's look at the limit of this expression when n tends to infinity. So when n tends to infinity, this limit is equal to the product between this constant and the limit of this term. Now L is between 0 and 1 is excluding 1, so this limit will be 0. And so this entire limit here is also 0. Therefore, by the squeeze theorem that will show up again, when we take up the limit of this to when n tends to infinity, so the limit of 0 when n tends to infinity is of course 0. And now we've seen that the limit of this term when we take n to infinity, then we take n to infinity, will also be 0. So because of the squeeze theorem, we'll know that the limit of this term when n tends to infinity will also be 0. So by the squeeze theorem, we have shown that this limit is 0. Now, what is this limit? This limit is precisely the definition of a Cauchy function. So because this holds, we know now that our function v0, v1, v2, and so on is a Cauchy sequence. Okay, so remember that in a Cauchy sequence, there exists an n such that for any n larger or equal than n, sorry, let me start. So there is, for any epsilon larger than 0, there exists an n such that for any n larger than that n, the maximum difference in norm between a vector n and a vector that follows it in this sequence will be less than epsilon. So we have just shown that. So let's go back and see what we've shown so far. So we have shown so far that if we have a Banach space and we have an L contraction on this Banach space, we have shown so far that the sequence that results from applying to an arbitrary initial vector this transformation T is a Cauchy sequence. That's all that we've shown so far. Now, if because you're in a Banach space, every Cauchy sequence converges to some vector v. Remember, that's the definition of a Banach space. And so let's denote by v the vector such that this sequence converges to. So let's denote by v the vector that our sequence of applying the same operator over and over again to an arbitrary starting point converges to. So all that we know that is that our sequence converges to a v now. Our next step is to show that v is a fixed point of t, meaning that when we apply to v or transformation T will stay at V. Okay. So now we will use uh, our loved trick of introducing zeros again. So we know that 0 is less or equal than the norm between two vectors. That's always the case. And the vectors in question are the transformed version of our fixed point and of what we believe is a fixed point, so we haven't shown yet. So V is just, for now, just the vector to which we know our sequence converges. And we know that happens because our sequence is Cauchy and we are in a Banach space. So let's see what is the norm between this vector V and its transformed version TV. Of a norm of the difference between our vector V and its transformed version TV. Well, let's introduce zeros again. So in this time, we're going to introduce zeros by introducing for an arbitrary n in our sequence, the result of transforming the vector Vn and minus the result of transforming the vector Vn. So remember, this will add up to 0 for any n that we pick. So pick just an arbitrary n for now and put these two terms, the transformed version of Vn and the minus the transformed version of Vn. Of course, when we add this 0 vector here to these two vectors and compute the norm, nothing changes. But we can then use the triangle inequality. So basically, we're going to use the triangle inequality to consider these two pairs of vectors separately now. Okay. So clearly, by the triangle inequality, this norm is less or equal than the sum of the individual norms. Okay. And now, because T is an L contraction, this the sum of these norms must be less or equal than the sum of L times the norm between V minus Vn. So now what we're doing is we are comparing the norm of the transformed vectors to the distance between the transformed vectors and the distances between the original vectors again. And here we're just using the definition of Vn plus 1 to arrive at this vector. So these terms here are equal. And we know from the definition of an L contraction that this term here must be less or equal than this term. Now, what I want you to note is that because our sequence converges to V in norm, if you take the limit of this term when n tends to infinity, you have 0. Why? Well, that just comes directly from the definition of convergence in norm. So we know that, so convergence in norm, remember, tells us that V minus Vn, the limit when n tends to infinity, that's 0. So this limit here is clearly 0, and this limit is also 0 by simply calling this n plus 1 here, right? Okay, so by the squeeze theorem, again, the squeeze theorem becomes useful because we know that the limit when n tends to infinity of 0 is 0, and the limit of this term when n tends to infinity is 0. We also, it also must be the case that the limit when n tends to infinity of this norm here is 0, which implies that the norm of TV minus V is 0. So if you see me pausing the video sometimes, it's because I'm looking for the best way to explain a concept. So If you are confused about why this is the case, just remember that if you have a constant, a, for example, the limit when an n that doesn't affect a constant tends to infinity, the limit of this constant when something that doesn't affect it tends to infinity will simply be the constant itself. Okay. So by the definition of norm, the only way for the distance between TV and V to be 0 is if TV is equal to V. Okay, so we've completed the proof that V is a fixed point of our is a fixed point. So remember what we've, so now let's look at what we've proved so far. So if we have a Banach space and you have an L contraction on this Banach space, we have proved that if you start a sequence at some arbitrary point, we've proved that this sequence will that if and if you keep applying this transformation for each element of this sequence, we have shown that this sequence will converge in norm to some vector v, and we have just shown that this vector v is a fixed point of this transformation. Now we're missing one step here. We haven't proven yet that this fixed point is unique. Now, in order to prove that the fixed point is unique, let's suppose that we have a fixed point called u of this t, and let's suppose that we have a fixed point called v of this t, okay? So now we're going to show that these fixed points must be actually, that these different names must actually refer to the same point. So let's look at the difference between, at the distance between these 2 points. Well, the distance between these 2 points, because they are fixed points, must be equal to the distance between the transformed versions, because u is equal to tu and v is equal to tv by assumption. And we know from t being an L contraction that this must be less or equal than a constant L times the distance between u and v. Okay? So now let's suppose that the distance between these 2 points is larger than 0. So let's suppose that the points are different. So if the points are different, if we divide both sides of this inequation by the norm of u minus v, we will have the conclusion that L is larger or equal. So it will look like this. L will be larger or equal than 1. So we've divided this term by itself, and we divided this term by this term. And so then we will reach the conclusion that 1 is less or equal than L. However, T is an L contraction, so this is a contradiction. L cannot be larger or equal to 1. So again, we wanted to show that a fixed point of T would be unique. So we picked a nu that is a fixed point, and we picked a v that is also a fixed point, and we wanted to show that these names refer to the same vectors. Now we looked at the distance between these 2 points, and we've seen that it would be equal to the distance between their transformed versions, and that distance needs necessarily to be less or equal to L times the distance between the 2 vectors. However, if we suppose that this distance is larger than 0, we would reach a contradiction, because L would need to be larger or equal to 1. Therefore, the distance between these 2 vectors must be 0. So this cannot be the case. So because it cannot be lesser than 0, it must be 0. Okay? And now if the distance between the vectors are 0, they must be equal. So we have proven that no matter which 2 points we pick, if they are fixed points of T, then they must actually be the same point. And our last step is to show, so remember there's only one last thing now to show that we promised to show about Banach's, that we promised to show in Banach's fixed point theorem. We promised to show that the distance between the convergence point V and our vector after n time steps will be less or equal than L to the n times the distance between V0 and our point of convergence. Now the case L equals 1 is trivial again because we just need to prove that V0 minus V is less or equal than L to the 0 times V0 minus V. Well, that's obvious, this is 1. So we just need to prove that something is equal to itself. Now let's use induction here again. So let's assume that this statement is true for n, and let's prove that it's also true then for n plus 1. So let's look at the distance between the point Vn plus 1 and the point n and the point V. By our definition of our sequence, Vn plus 1 is equal to the result of transforming Vn. And by our definition of by the definition of fixed point, Tv will result in V. So these two quantities are equal. And once we have, and by the definition of an L contraction, this value is less or equal than L. So the distance between the transformed version of these points is less or equal than L times the original distances between these points. And by our inductive hypothesis, this distance between Vn and V must be less or equal than L to the n times the distance between V0 and V. So we can place instead of this term, we can replace this term by this term, and we will have this inequality still holding. So this is the result of multiplying this L by this L n here. So we've managed to prove then, we've proved by induction that this is the case for any n. So we've proved that this is the case for n equals 0. Then we assume that this was true for an arbitrary n, and that allows us to prove that it would also be true for an n plus 1. And finally, we have finished proving Banach's fixed point theorem. So after all of this work, let's take a look again at the theorem and see what we've managed to prove. So if we have a Banach space Z with this norm, if we have a Banach space Z with this norm, meaning that this is a normed vector space where every Cauchy sequence converges to some vector, and we have an L contraction T that maps vectors from this space to other vectors of this space, then this T will have a unique fixed point V. And furthermore, if you start a process where you start at an arbitrary, with an arbitrary vector in this space, and you define the next vector in a sequence by applying the transformation to the previous vector in the sequence, then the sequence will eventually converge in norm to this fixed point of T. And the speed of convergence is explained by this inequality here. So the distance between your original point and the fixed point times L to the n must be less, or it will be larger or equal than the distance after n time steps. So after n time steps, your distance must be smaller than the original distance times L to the n. So the smaller the L, the faster you will converge to the fixed point. So how can we use Banach's fixed point theorem to prove the convergence of iterative policy evaluation? So first of all, let's try to remember what we are trying to prove here. So consider the Bellman operator, T pi, which, as you remember, represents the computation that policy evaluation performs in order to update the estimate for a value of a state into the next estimate, and so on. So given an arbitrary vector v0, I want you to consider the sequence that is obtained when you successively apply this transformation. So you have a sequence where you start as an arbitrary v0, and you obtain v1 by applying the Bellman operator to v0. You obtain v2 by applying the Bellman operator to v1, and so on. And let me also denote by v pi the vector that represents the value function for the policy pi. What I want to show is that this sequence resulting of applying the Bellman operator converges in norm, in maximum norm, to the vector v pi. Furthermore, I want to prove that v pi is a fixed point of this Bellman operator. And finally, I want to prove something about the speed of convergence of this sequence. So after n time steps, my distance in maximum norm to the fixed point will be less or equal than gamma, the discount factor, to the n times the distance between my original estimate and the fixed point. So the closer I start my estimates to the fixed point, the closer I will be after n time steps. And the closer to zero my discount factor is, the faster I will converge as well. This is what we are trying to prove. So as a first step, we are going to show that v pi is a fixed point of the Bellman operator. This is actually very easy. So if you go back and see how I defined the Bellman operator, you see that once I apply this Bellman operator to a vector that represents the value function for a specific policy, what I will get for any given state will be precisely the value of that state given that policy. Because remember that we defined the value of a state under a specific policy as this expectation over what's the probability of taking each action for that state times the expectation over every possible next state of the probability of transitioning from the original state to that state given that action, times the immediate reward and the return that you expect from that state onwards. So just from the definition of the Bellman operator that we found way back, I'm not going to return to that, but from the definition of the Bellman operator, we see that applying it to the value function for a specific policy will give us back the value of that function again. So if we apply tpi to vpi, we are guaranteed to get vpi by how we defined vpi, okay? And tpi, of course. So we've shown that vpi is a fixed point of tpi. This was very easy to do. It just came straight from the definitions of these two things. Now the next point that we need to prove is that the Bellman operator is a gamma contraction. So if we prove that the Bellman operator is a gamma contraction, because the vector space that contains the vectors that represent our value function under the policy together with a maximum norm is a Banach space. So remember that I've told you before that for any d, for any number of dimensions, the vector space, the real vector space with that many dimensions together with a maximum norm is a Banach space. So because this space here together with the maximum norm will be a Banach space, and because we know that vpi is a fixed point of tpi, if we are able to show that tpi is a gamma contraction, we will show that the result of successive applications of this function tpi in order to obtain a sequence of estimates of the values of the function, we know that it must converge, right, from Banach's fixed point theorem. We know, first of all, it must converge. It knows that it must converge to a fixed point, okay? And we know that this fixed point is unique. So because we've already shown that vpi is a fixed point of tpi, we know that if t is a pi contraction, when this process will need to converge, and it will need to converge to this fixed point uniquely. So all that remains after all of this work is for us to show that the Bellman operator is a gamma contraction. So let's see how that can be done. The first thing that I want you to notice is that if you have any arbitrary vectors u and v, for any state, the following will hold. So the difference between element s of the result of applying t of pi to u and the result of applying t of pi to v, the element s of applying. So let me go over this again. So for any two vectors u and v and every state s, you can see that the result of subtracting the element s from the vector that results of applying t pi to u, from subtracting from that the element s of the result of applying t pi to a vector v is equal to this this subtraction. So I'm splitting this across two lines here, but this term corresponds to the first. Is simply the definition of accessing a specific state that results that is encoded into this vector, and this is simply the result of accessing a specific state from the vector that results from this operation. This comes straight from the definition of the Bellman operator. So I want you to notice that this subtracted from this can be written as follows. So basically what you can do is you can distribute so basically you can distribute this term inside this summation. So you end up with this term times this term plus this term plus times this term times this term. And you can then furthermore, you can then distribute this term over this as well. Then you have multiplication of this term by this term by this term, plus a multiplication of this term by this term by this term. Okay? And once you do that for both summations here, you'll be able to rewrite them as the following difference, because basically these terms, the terms that you distribute, I think this is maybe clear already to you, but basically the only difference between these two summations is here and here. So you'll be able to split these summations in such a way that some of the terms will cancel each other out, and you'll be left out with this summation. This is a very easy detail. It's just a little bit hard to explain without showing you every step. And it, as you can note, is quite cumbersome to draw everything using my mouse here. Okay, so once you have these two terms here, you can actually rewrite this very easily. So first of all, you can note that this term, this factor here is a constant, so you can push it outside of the summation in both for both summations here, which means that you can place it before all of them, so you distribute it between them. And then you also note that you can write this basically using a single, basically you can transform these two into this summation here. These are all very, very simple manipulations that you can do, but basically just note that you can, write this difference as in this way, okay, for now. So let's go to the next step then. Now remember, the only thing that we want to prove, the very last thing that we want to prove after all of this work is that T of pi is a gamma contraction. So now we are ready for the absolute final slide in this proof. Let's see. So by the definition of maximum norm, for any two vectors u and v in our vector space, the maximum norm of the difference between T of pi applied to u and a T of pi applied to v will be the maximum across all states, so across all elements of the vector that is the difference between these two vectors. And so the maximum norm, remember the maximum norm of a vector, let's say the maximum norm of a vector v is the maximum in absolute value, the maximum element in absolute value of that vector, okay? So just using this result that we've seen in the previous page here, that for any two vectors, you can write this difference in this way, we can show that the element of the vector, that basically every element of this vector that is the result of subtracting these two vectors can be written in this way here. And now, so basically what we did is we simply used this result and we moved the factor gamma outside the maximum operation. We can do that because gamma is a constant. And the S here has this absolutely the same role as the I has here, if that's not clear to you yet. So from this comes from the definition of maximum norm. And then we can use the triangle inequality to show this next step here. And the triangle inequality in this case refers to the triangle inequality that applies to the absolute value. So if you have the sum of two values A and B in absolute value, that is guaranteedly less than the sum of the individual absolute values. Okay. So this is where this step comes from. So this introduces an inequality here. So this value will always be less or equal to this value here. And so from this step to this step, what's happening is that I'm noting that because this is a probability and because this is a probability, this must be a number larger or equal to 0. And so when I have A times B in absolute value, and I know for sure that A is larger than 0, then this will be equal to A times B. So this is the step here. And now there's one more step where I'm using the fact that the difference in absolute value between U of S prime and V of S prime will be less or equal than the maximum norm between the vectors U and V. So this comes straight from the definition of the maximum norm. So remember, the maximum norm of the difference between these two vectors would basically pick the maximum possible value of US minus VS in modulo across S's, right? So this would be the maximum norm between these vectors. So this value here for sure is larger than this value here, because if this value were larger, it would be the norm, right? And so what we can see now is that this norm here is actually a constant with respect to the choice of S, is completely constant with respect to the choice of S. So we can not only move this constant here outside of all of the summations because it's a constant with respect to A and S prime, but also outside the maximum operation because it is a positive, a non-negative number that does not depend on S at all. So that's how we get to this line here. And now we just need one more step and we'll be done. So what you need to notice now is that this is the probability of transitioning from a state S to a state S prime given an action A. And if you sum this probability over all possible S primes, then this must be 1, right? Because the probability of transitioning to some of the states to some of the other state must be 1. So if you sum the probability of transitioning to each of the states, you're going to add up to 1. This just comes from the unit measure property. And this similar thing happens here with this. So after you conclude that this is 1, then you're just looking at a sum over all possible actions of the probability of transitioning in a specific state taking that action. So if you sum that over all actions, because you need to take one of the actions, the probability this must also be 1. So the maximum over all S of 1 is 1. And so you have just a multiplicative term of 1 here, which lets you conclude that the difference in maximum norm between the transformed versions of U and V, the transformation being made by the Bellman operator, is less or equal than gamma times the norm between U, between the norm of the difference between U and V. So in other words, when you transform any two vectors U and V by the Bellman operator, and you compute their distance in maximum norm using the maximum norm, then that distance will be less or equal than the original distance in maximum norm between those vectors times a gamma. And because this is the case, we've proved that T pi is a gamma contraction. And by having shown that um, uh, T of pi is a gamma contraction, we've met all the necessary conditions to apply Banach's fixed point theorem. So let's go back one last time to the statement of the theorem to make sure that we've proved all that we needed to prove. So consider the Bellman operator, T of pi for the policy pi. Given an arbitrary vector v0, consider the sequence that results from sequentially applying this T pi, and let v of pi denote the value function for this policy pi. Now, we have shown that this sequence converges in maximum norm to v pi. We have shown that, and we've done that by showing that, um, by showing a few things. I'll go over them in a minute. We've shown that v pi is a fixed point of T pi, and we have shown something about the convergence speed of this sequence to our v pi. So basically what we did is we showed that T pi is a gamma contraction. We have shown that v pi is a fixed point of our gamma contraction. And because we are living in, and we have shown that the sequence that we have is converging to v pi. So because we are living in a Banach space, so let me try to relate this result to Banach's fixed point theorem now. So coming back to Banach's fixed point theorem, we knew that if we had a Banach space and an L contraction, we would know that that L contraction would have a unique fixed point. And if we had any sequence resulting from iteratively applying that transformation, that sequence would converge in norm to the fixed point at a certain speed. So in order to use this theorem to prove the convergence of iterative policy evaluation, we have simply shown that T pi is a gamma contraction. Then we have shown that v pi is a fixed point of that transformation. And as a consequence, because we know that that a sequence of this form has to converge to that fixed point, we then were able to show that the sequence obtained by applying this operator to an arbitrary estimate of value for a policy will eventually converge to the value of the policy. So that's Banach's fixed point theorem applied to the proof of the convergence of policy, of iterative policy evaluation. If you want another, so this proof you will be able to find in my notes on reinforcement learning, and you'll also be able to find it on the book Algorithms for Reinforcement Learning. Now remember, the first edition of the book does have a mistake, so be careful. So congratulations if you've managed to follow the proof so far. And I hope that you've enjoyed. Even if only a few of you are able to enjoy this proof, I'll already be quite happy. So thank you very much, and I'll see you in the next lecture.